Nora is going to talk about bridging the gap to auto-formalize free-form human reasoning.
Hi everyone, my name is Nora, so I'm a Berkeley graduate student. Today I'm presenting about bridging the gap to auto-formalize free-form human reasoning. So I'm interested in understanding how human can interact with a verified AI system in a natural and organic way. So specifically, this project is around auto-formalization in math educational context. So we are interested in building a formally verified AI system where a human can interact using pure natural language without having any knowledge about formal verification. So our use case, Lean Tutor, we allow a student to enter their proof in natural language, and then we translate, which we also call auto-formalize, their proof into Lean. And then we use a compiler to compile this proof, and then we informalize this compiled proof back to natural language to give them feedback. So this creates a seamless co-reasoning system where the student can have no knowledge about Lean. So recently, the latest LLM seems doing quite a good job in auto-formalization. However, in real-world context, auto-formalization is still a very challenging task because, firstly, the standard auto-formalization benchmark mainly contains just polished textbook-style natural language proofs. However, the proofs that students have written are like this. They are more diverse, free-form, nonlinear, implicit, and causing the LLM cannot auto-formalize it correctly. So in these three examples, the students are all approaching a same question with the same strategy, and they are all correct proofs, but they all look so different. So the problem becomes, how can we understand and formalize such free-form and implicit reasoning? Another challenge for auto-formalization is faithfulness. So current models primarily emphasize on proof completion. However, in an educational setting, completion is actually not the goal. If the student proof is incorrect, the auto-formalization should also be incorrect. If the student proof is incomplete, the auto-formalization should keep incomplete instead of auto-complete the proof. So that is another challenge. So for example, this is an example. So this is a step written by a student. So in the first step, the student just explaining in detail how is one formula translated to another formula. But in the later step, the student just write by similar reasoning. And by this term, by similar reasoning, the student is just trying to apply the same strategy that applied before into this formula. So that within the auto-formalization, we should also use, the later proof step should also use the same strategy as the earlier proof step. However, we'll show that in a baseline auto-formalizer, LLMs always fail to do that, to use the same strategy. So we ask, how might we faithfully auto-formalize free from human input? So within this work, we contribute firstly a taxonomy of ambiguities in free-form natural language that make the auto-formalization challenging. And secondly, we also introduce a system which we call a pre-processing system designed to reduce such ambiguities. And thirdly, finally, we evaluate this pre-processing system using our auto-formalization decision system. So first we ask, what kind of ambiguities in natural language proofs prevent an LLM from correctly auto-formalize the proof? So to answer this, we conducted a formative study. So we collected 24 student-written proofs like this. And first step, we manually formalize all the proof into faithful Lean code. And then second step, we also use a baseline LLM, just a LLM with basic prompting, to try to auto-formalize them into Lean. And as expected, this version contains multiple errors. And then to identify where the error occurred, we compare these two versions step by step. Through this comparison, we can then identify the natural language step that contains ambiguities that make the LLM cannot auto-formalize it correctly. So next, we apply some reflexive semantic analysis to cluster these ambiguities into 4 categories. So we will introduce these 4 categories one by one. So the first type is reference ambiguities, which occur when a proof step use a pronoun or referential term. And then the second type, we call it operation ambiguity. So it occurs when a proof step lacks a clear keyword indicating whether it is assumption or it is a declaration or assertion. So in this example, by writing the first line, the student is trying to make a declaration which is considered C such that dx equals C. However, it is not clear without any context. And next step is what we call antecedent, consequent, and evidence ambiguity. So this ambiguity arises when it is unclear what is the antecedent and what is the consequent within one proof step. And the final type of ambiguity is what we call granularity ambiguity, which concern about the level of detail provided in a proof step. So often, like in the formal language such as Lean, require like much more detail than what is commonly accepted as rigorous in a human written proof. So now we have identified our like 4 types of ambiguities in free-form like student written proofs. And the next question is, when these ambiguities are presented, how can we still understand and formalize student reasoning? So this is the envision system that we mentioned earlier. And this is the auto-formalization part that we focus on. Now we introduce a pre-processing system that take in the free-form natural language proofs and produce a less ambiguous version that an LLM can auto-formalize into Lean. So this is the structure of the whole preprocessor. It contains 4 layers, each corresponding to one type of ambiguities. And each layer is designed to like solve one specific ambiguities that we mentioned earlier. So layer 1 to 3 are LLM based and layer 4 are Lean supplements. So after this 4 layer of preprocessor, the output is then passed to an autoformalizer, which is largely identical to our baseline autoformalizer. And following this autoformalization, we include a syntax repair layer after the compiler output. It takes in both the error message and the generated Lean code to attempt one try on like repairing the errored code. So we evaluate the accuracy of the preprocessing system using 2 metrics. The first metric is autoformalization accuracy. So we define a step as successfully autoformalized even only if it is both compiled and it is faithful. And using this definition, the baseline success rate is like 45%, and the preprocessing success rate is 78%, and with a layer 5, like the autocorrection, it is 88%. We also evaluate the individual accuracy of our LLM-based preprocessing layer. So here's the layer-wise accuracy. We recognize that the layer-wise accuracy is have a large range. So we also like manually go through like what are the failure case of like each layer. We do not have so much time in the talk to talk about this, but I'm happy to talk about them later. So now with the preprocessing in place, what comes next? So wait, why is it? Basically, as we mentioned, like a long-term goal of a Lean tutor is to build an interactive co-reasoning agent. So here's a demo of the agent that we are currently building. So basically, the student can enter a proof here by taking an image, and we have an OCR to take the image. And then here's the proof, and then they can double check whether the OCR is correct, and then they can click verify the proof. And here we can see, okay, this is the verification result. On the right, we show like each step whether their proof is correct or not by showing them like all the claims that we break down. And they also got their error message, which in this case we just show like, okay, their proof is correct so far, but it's not complete. Okay. So how is the preprocessing pipeline applied in this interface? So each substep is classified as either a claim or an assumption. A separation is handled by our second layer, which is the operational classification layer. And a larger claim, like the second step, is also divided into multiple smaller claims. And this is done by our third layer, which is the antecedent, consequent, and evidence layer. And additionally, the pronoun terms, which the student use in the proofs, appear highlighted. And when you hover over it, it will display the interpretation of what we think the pronoun referred to. So that is how the preprocessing is applied in the current interface. And currently we are doing like more user studies to evaluate both the usability and the usefulness of the link tutor. And we hope in the future we can generate a deeper analysis of the system itself. And that is all my collaborators. And here's some questions to get started. And here's also my slides in the QR code. And thank you so much for listening.
So humans often do proofs at a higher level of abstraction than theorem provers.
Yeah.
And one of the feedback that your tool can give to students is that they missed a step, which is great. Except, what if the step they missed is just them working at a higher level of abstraction?
Okay. That is a really great question. So currently in our interface, in our platform, we self-define what is a larger gap and what is a smaller gap. So basically, I mean, like this granularity issue is like a quite challenging issue because this granularity is subjective. So basically, different class have different different granularity. Like in a basic linear algebra class, the teacher expects the student to express in a more detailed way. But in a higher class, like this granularity is not an issue anymore. So basically, yeah, I think the granularity, which is gap, like what is the link code accepted that the student should skip, should be like self-defined.
Do you have an approach for doing that? Or
well,
is that future
basically,
work?
I think Arno?
Yeah, I can answer that question. So the way we do this is, so each of those translations that are created are actually proved in Lean. We give the prover a set of axioms that we define to be granularity something. So axioms are steps that we would allow as a key step in a proof. If the Lean proof uses more than two of those key steps, then we define it to be a large jump. We understand that our prover might just sidestep the axioms and prove it directly using schematic or like core Lean, which is definitely something we're working on. But it's a pseudo way of catching this large jump.
Yeah.
Thanks.
This haven't been like well tested. We are still like doing new study to see whether this approach is great.
The preprocessing step is actually really cool. So I was wondering if it'd be a good idea for, whereas the natural language to Lean path is using LLM, the Lean to natural language step would be used classical linguistics, so we can verify that the text generated matches the Lean absolutely correctly.
Yeah, we are definitely thinking about it, and I think it's a good approach. Basically, like you're saying, that informization should be done mechanically using some. Yeah, that is something that we are saying, and yeah, it's really a great insight about. Yeah, we need to try about this.
So I have a question about like it proofs written in like Lean to prove like typical theorems students solve actually match the handwritten style. So like, have you actually created like custom tactics to match those kind of handwritten proof style, or like is it already like typical Lean proofs look like handwritten proofs?
I think there's a faithfulness issue. Basically, in our interface, if you can see, we have a button here, like this is what I mean, and this is not what I mean. So basically, we are definitely using LM to create a link code, and then we are trying to let users to judge whether this is a good representation of their writing. If not, they need to change their writing. Yeah. But basically, I'll say like at least for the equational based proofs, it's normally well represented. Yeah.
Great, thank you.